Hi, I'm Hongyi Hu. In this video, I'll show how frozen LiDAR features can support off-road autonomy, especially when sun glare challenges the camera. Off-road autonomy depends on understanding terrain when the environment is least cooperative. In this work, we ask whether a frozen LiDAR native encoder can provide useful geometric-semantic features to an existing autonomous stack without redesigning the downstream network or learning objectives. We integrate Utonia into two different systems, Salon for local traversability cost and speed estimation, and Travesuite for bird's eye view terrain prediction and navigation evaluation. The key result is not that one feature source wins everything. It is that frozen point cloud features can be made reusable, can be run at a practical operating point, and can remain more stable than image features under strong sun glare, while the effect on downstream behavior remains mixed. An interface gap between point cloud representation learning and off-road autonomy. Modern 3D encoders produce rich hierarchical embeddings for points. They're commonly evaluated on segmentation, detection, or linear probe benchmarks. Existing autonomy systems, however, are not waiting for a 384-dimensional feature at every point. They expect compact channels attached to points, voxels, or a bird's eye view grid, and those channels must pass through established training and planning code. Replacing the whole system would make it difficult to tell whether the representation or the new architecture caused a result. Our approach is deliberately narrower. We keep Utonia frozen, preserve the existing Salon and Travesuite architectures, and add only the adapters needed to map Utonia's features into the interfaces those systems already consume. Utonia is a point transformer V3-based encoder trained across heterogeneous point cloud domains. We use the encoder only. Its weights are frozen, and a LiDAR scan optionally aligned with RGB enters Utonia and produces hierarchical 384-dimensional point embeddings. Pooling parent bookkeeping maps the encoded features back to the original points, after which the existing stacks aggregates them into voxels. From there, the two downstream systems need different adapters. Salon has an existing 8-channel terrain feature interface, so we fit 8 k-mean centers and represent each point or voxel by its distances to those centers. Travesuite needs a compact BEV input, so principal component analysis compresses 384 dimensions to 33. Those used Utonia channels are then concatenated with existing radio image features. Superodometry supplies the poses used when scans are accumulated. The important design constraint is that Salon's Gaussian process and Travesuite's prediction and inverse reinforcement learning objectives are not changed. Downstream systems expose different failure modes. Salon is an online local adaptation system. It uses terrain features and proprioceptive feedback in a radial basis function Gaussian process to estimate local roughness, cost, and speed. Here, useful features should produce coherent local maps and should remain consistent when the same terrain is observed from different ranges. Travesuite asks a broader question. It predicts BEV terrain quantities, completes terrain using hindsight supervision, and evaluates navigation with a maximum entropy inverse reinforcement learning objective. A feature source might help expert trajectory likelihood while hurting speed prediction, or help geometric completion without improving path shape. Testing the same frozen encoder in both systems makes it harder to mistake one favorable metric for a general claim about autonomy. Efficiency, representation stability, and downstream task behavior. The Salon analysis uses a 5081 frame figure 8 route with severe sun glare. The main Travesuite comparison uses full Gascola, while a second Travesuite evaluation returns to the figure 8 sun glare route. This separation matters. The runtime sequence measures an engineering trade-off, not navigation quality. The fixed patch salon experiment measures self-consistency, not ground truth terrain accuracy, and the Traversability tables measure offline navigation and prediction metrics, not closed-loop vehicle behavior. Keeping these questions distinct lets us make claims that match the evidence rather than blending several partial results into one stronger but unsupported conclusion. The internal voxel grid controls a direct trade-off between compute and feature fidelity. We compare the dense 0.01 meter reference against 0.02, 0.025, 0.03, and 0.04 meter grid over all 993 frames. Every condition completes without failure, and all grids preserve the evaluated support. The selected 0.025 meter setting reduces end-to-end time from 0.357 to 0.195 seconds per frame. Throughput rises from 2.8 to 5.13 frames per second, a 1.833 times speedup, and 45.5% lower latency. The cost is a representation change. Voxel cosine similarity is about 0.65, and Bev cosine similarity is about 0.7 relative to the dense reference. Coarser grids are faster but move farther from the reference. This point is therefore an engineering compromise from one controlled execution, not a claim that 0.025 meters is universally optimal or that 5.13 FPS is yet sufficient for every deployment. The experiment follows fixed world regions as the vehicle approaches or moves away. Candidate patches are placed every 10 meters along the route. Every patch contains 5 by 5 cells, requires at least 9 common valid cells, and limits the bearing difference to 45 degrees. Of 259 candidates, 172 patches have complete observations for both radio and raw 2-frame Utonia through 40 meters. Measurements are grouped into 5-meter arrangements. The 0 to 5 meter bin is the reference, but it is only a near-range self-consistency estimate. It is not a ground truth. Features are scaled by the standard deviation in Salon's initial Gaussian process training buffer. We then compute feature cosine drift, Gaussian process normalized feature root mean square error, and absolute cost drift. Uncertainty comes from 10,000 paired bootstrap resamples with seed 0. Presentation level, the result is consistent across the measured range. Raw 2-frame Utonia has lower cosine drift than radio in every non-reference bin. At 35 to 40 meters, radio's median cosine drift is about 0.071, while Utonia remains below 0.001. The paired bootstrap interval excludes 0 in every bin. The magnitude result points in the same direction. At 35 to 40 meters, GP normalized feature RMSE is about 1.412 for radio and 1.032 for Utonia, and again, every paired interval excludes 0. These are strong self-consistency results. The LiDAR native representation changes less in direction and magnitude as range increases under the singular conditions in these routes. They do not prove that the features are correct, and they do not establish robustness to darkness, dust, smoke, or weather because those conditions were not directly evaluated. The downstream cost result is the critical qualification. Although the Utonia representation is more stable, the paired interval for absolute Gaussian process cosine drift includes 0 in every arrangement. In other words, this experiment distinguishes the input features but does not distinguish the final cost outputs as the chosen significance level. That is plausible because a Gaussian process with a RBF kernel is a smoothing model. Different feature perturbations can map to very similar predictions, especially when the data and kernel length scales dominate the local variation. The broader lesson is important for foundation features. A cleaner or more stable embedding is not itself a navigation result. We need to trace the signal through the actual downstream consumer and ultimately through closed-loop behavior. It compares 4 sources: radio alone, radio plus RGB aligned raw-to-frame Utonia, radio plus no color raw-to-frame Utonia, and radio plus observed voxel Utonia. LiDAR history is excluded because its runtime is impractical. The evaluation spans 3 metric families. Navigation includes expert log probability, expert log goal probability, and modified Hausdorff distance between trajectories. Speed uses Earth mover's distance squared and speed probability. Hindsight prediction reports geometry, terrain, slope differences, and visual feature errors. Within navigation, all 4 sources are identical sample identifiers. The same is true within hindsight, but the navigation and hindsight sets are different. In Folk-Escola, they overlap in only 1 sample, and in the singular evaluation, they do not overlap at all. These columns are complementary views of performance, not a matched joint comparison. Folk-Escola navigation set contains 1,824 samples from 47 runs, and the hindsight set contains 2,161 samples from 48 runs. All checkpoints use seed 42. The result is a trade-off rather than a ranking. Observed voxel Utonia has the best expert log probability and the log goal, with an expert log probability of about minus 10.99 compared to minus 11.42 for radio. Radio, however, has the lowest modified Hausdorff distance and leads both speed metrics. No color Utonia has the lowest geometry, terrain, and slope hindsight errors. RGB Utonia has the lowest visual feature error, although the differences in several hindsight columns are very small. This pattern argues against a universal Utonia beats radio claim. Accumulated geometry may align better with the expert trajectory objective, while image features preserve advantages for path shape and speed. Geometry-only features help several terrain completion metrics, and RGB conditioning does not consistently dominate no-color input. Simple feature concatenation may also limit cross-model interaction. Taking together, the experiments support 4 claims. First, frozen Utonia features can pass through existing point, voxel, and bev interfaces. Second, internal grid size exposes a measurable runtime fidelity trade-off with a usable selected operating point. Third, raw two-frame Utonia is more stable than radio at the representation level on the evaluated singular route. Fourth, Utonia can qualitatively produce better cost map results with salon than radio under severe lighting conditions. Several stronger claims are not supported. We do not establish universal downstream superiority. We do not test darkness, dust, smoke, rain, or snow directly. Traversability uses one seed, and navigation and hindsight are not matched sample sets. Most importantly, no closed-loop rollout demonstrates that the feature stability improves vehicle behavior. The honest interpretation is that they complement each other. LiDAR native features add a different signal, but they do not yet replace image features or settle the navigation question. Work should close the gaps in that order. First, repeat training and evaluation across seeds to test whether the source rankings are stable. Second, evaluate navigation and hindsight on matched examples or report route level uncertainty so metric relationships can be analyzed directly. Third, replace simple concatenation with learned fusion, cross-attention, or modality gating, allowing the system to change how much it trusts image and LiDAR features. Finally, run the learned costs through MPPI and evaluate on-vehicle closed-loop trials. That experiment must measure task outcomes such as intervention rate, progress, path quality, speed, and safety under controlled sensing degradations. Only then can representation stability be connected to autonomy performance. Current contribution is useful infrastructure and a careful bounded result. Utonia's 384-dimensional point embeddings become compact inputs for two existing autonomy systems. A 0.025 meter grid reaches 5.13 frames per second at 0.707 Bev cosine similarity on the control sweep. Under the evaluated sun glare, Utonia features drift less with range, while the downstream benefits remain source and metric dependent. The next answer must come from closed-loop behaviors. Thank you for listening. This work was conducted at AirLab through the RISC program at CMU. Thanks to Wenshan Wang, Sebastian Scher, Matthew Silvercrossum, and the Off-Road Autonomy Group, the broader AirLab community, Rachel Burson, Dr. John Dolan, and the peer reviewer for their mentorship, guidance, support, and feedback.